So I'll continue where I left the lecture yesterday, and I'll actually remind you a little bit of what I did the last bit of the lecture, using some transparencies. The end of the lecture, I explained that the S matrix, which describes the relation between the initial state and the final state, can be expressed in terms of the interaction Hamiltonian, and the way it goes, I'll remind you of that. Actually, because what we did, we looked at the Schrödinger equation not for a single particle state, for the full state of many particles, in particular the particles that start in the initial process that come in. And then the solution to the Schrödinger equation can be written in terms of, well, an evolution operator. Sometimes, usually this operator is written with the symbol U, so it's sometimes called the evolution operator. It describes the relation between the state at an earlier time t prime and the state at a later time t through an operator u, which depends on those both times. And since this state psi satisfies the Schrödinger equation, which means if I differentiate with respect to the time, it gives you the Hamiltonian acting on the state, this operator should satisfy the similar relation. This operator, if you differentiate it with respect to time, t, it gives you the Hamiltonian acting on this operator, but it depends on two times. It depends on the time t and the time t prime, which is the initial time from which we evolve to the time t. So I can differentiate with respect to the later time t, and then the Hamiltonian acts on the left. If I differentiate with respect to the t prime, the Hamiltonian acts on the right. And this is important, that there's an ordering in time, because this is a later time and this is the earlier time. So operators which are at an earlier time act first. So they are on the right, and operators which act on a later time are on the left. Now we are interested in a relation between the in states and the out states. And the in states we define indeed as the time to minus infinity limit of the wave function psi of t, and the out state is the one that describes t to plus infinity. Now the S matrix is the matrix that relates in states with out states, and so formally it's equal to this evolution operator evaluated for t prime equals minus infinity and t equals plus infinity. And it's very important that since the norm of all of these states is conserved, that the S matrix is a unitary matrix, and it means that if you multiply S with its complex Hermitian conjugate, it should give you the identity matrix. And this condition is very important in quantum field theory, just to preserve probabilities. And conservation of probability is certainly a very important aspect of quantum mechanics. Well, the way we solved this operator and the S matrix is by looking indeed at this equation, actually the first equation which I have here, which you can solve in the following way. If you look at this equation, it tells you if you differentiate with respect to time, it gives you the Hamiltonian acting on it. And you can write that the solution in the form of this sum, which is actually should remind you of an exponential sum. And then there are these products of Hamiltonians ordered in such a way that indeed the earlier time acts first, etc. And we integrate over all times. And so I introduce this symbol t, which introduces the ordering of these products of Hamiltonians in such a way that first time comes first, and then we can actually integrate. If I introduce this symbol, that the order is always such that the time which is earliest in these integrals comes at the first position, then I can start integrating all of these t's from t to t prime. The only thing is that I'm overcounting if I would do it without any change in normalization. The fact that I put an n factorial here makes sure that the normalization which I have here is the same as I had here, where I had these restrictions on the times t. And so this indeed is the form of an exponential, and then I can write u of t prime as the time-ordered exponential of the integral of the interaction Hamiltonian. Now finally I can insert in this the fact that I know that the interaction Hamiltonian is the integral of some Hamiltonian density, the interaction part of it, and then I find eventually that the S matrix is the time-ordered exponential of minus I times the integral over space and time of the interaction Hamiltonian density. And this is the expression that if you then want to evaluate the transition amplitude from an initial state to a final state, is used actually as a starting point to derive the rules for computing those amplitudes. I'll switch to the board. Can I switch this off? Where do I do that? No, that's something else. So probably inside. Okay, thank you. So I'm now going to look at a particular process where we indeed have a certain initial state, and then we know, at least I wrote down here, the basic rule that gives you the final state. And just to write this down explicitly, we are interested in, say, a process where we have a number of initial states, initial particles, which have momentum pi, and we go to a number of final states which have momentum ki. Then we're interested in the amplitude, which gives you the overlap between the initial states P1 up to Pm, and final states K1 up to Km. And this overlap can be rewritten now in terms of this expression which I had over there as the inner product of these states Pi up to Pm. And here I denoted with the symbol I and F that these are states which should be taken first at t equals minus infinity and t equals plus infinity. And so here I write down the expression in terms of the Fock space which I introduced in the second lecture yesterday. And the expression which you get is that indeed you have to insert in here precisely the operator that represents the S matrix. Now, to evaluate this, what we do is actually expand again the exponential into powers of these interaction Hamiltonians, and then you have to just evaluate using the Fock space oscillator algebra all of these expectation values. And what you arrive at is, if you expand, then you arrive at the Feynman rules if you do it systematically. I will write down the Feynman, or give you the Feynman rules a little later, but for the moment we'll just leave this expression and just at least start from the point that we have at least a prescription to evaluate these amplitudes. Because what I want to do is first actually is to return to the fact that here I have an amplitude, but the thing that we want to compare to experiment is not the amplitude, but it's the cross-section. So just to go back to that fact that we have here a probability amplitude, which is something that we know how to calculate in quantum mechanics, but still is not really related to what things we measure in experiment. So there must be some translation be done from the amplitude cross-section. Well, in most situations, we're not looking really at experiments where we have a lot of particles that come in which collide and then gives you a lot of other particles. The usual situation is that you have two particles that collide, which indeed can give you lots of other particles, but it's very difficult to aim your experiment in such a way that you can have interactions between more incoming particles than just two. And indeed, the cross-section, sorry? Well, okay, so this is actually the state at t equals minus infinity, and that's the state at t equals plus infinity. And these states are actually defined in the same Hilbert space. And so what I have to do is insert the operator that maps the Hilbert space at t equals plus infinity to the Hilbert space at t equals minus infinity. And so this is the way that these two are related. Sorry, here I've indicated these are indeed at different times, while these states sort of are in the Hilbert space at the same time. So for a particular example, what I'm interested in is an amplitude which goes from an initial state to a final state where I have two incoming momentum P1 and P2 and a set of outgoing particles, say with momentum Km, K1 up to Km. Now this gives you the probability amplitude for a process where two particles with momentum P1 and P1 give you a set of n particles with momentum K1 up to Km. To get the full, to go to the cross-section, you have to use this amplitude to evaluate, first of all, the probability that something happens. And you know that in quantum mechanics, probabilities are not expressed as really expectation of inner products of this, but they are the square of an inner product. Furthermore, there are certain restrictions I have to put on, when this probability can vanish or not. It's because momentum is conserved that this probability can only be non-zero if the momentum P1 and P2, the sum of the two momenta, must be equal to the sum of the momenta that come out of it. So we have momentum conservation which is P1 plus P2 must be equal to the sum of all the momenta on the right that come out of it. And we also have energy conservation. And this means that if I take two particles, say of the same mass, just to simplify things a little bit, then I can calculate the frequency omega of P, which is related to the energy for the first particle and the second particle. Then these energies together, say it's an electron and a positron, we can use the same expression. Omega is the square root of k squared plus m squared. But then we can produce lots of other particles with other masses, and they must satisfy the equation that the sum of the momenta of the energies, which are functions omega I of the momentum ki, they must be equal. And this is just the fact that energy is conserved. And without these conditions, if these conditions are not satisfied, this amplitude will vanish. So inside the amplitude, we have something like a delta function that should impose those conditions. Actually, if you write down the probability amplitude in this way, we have to use it actually to go to the transition probability, which I'll denote with dW, which is a probability that indeed two particles with momentum p1 produce particles with momentum k1 up to km, but actually it's a probability only that we get particles in the range, in the area of these momentum between actually, say we have a probability that we get momenta ki in between the momentum ki and momentum in between ki and say ki plus dki. Some infinitesimal part of the momentum space is covered if you look at these amplitudes. So what I'm going to write down is actually the transition probability that we get in the final state of the particles, m particles with momentum ki in between ki and ki plus dki. And this probability, the transition amplitude probability, is equal to an expression which involves, first of all, the square of this amplitude, simply because we have to go to probabilities. And then in the quantum mechanics, we're used to square the amplitudes. And then I put in a normalization. And what we have to add to it is indeed the fact that we have indicated a certain region of momentum space, an infinitesimal region, and this we have to multiply this probability with the integration measure on this volume. So what I've written here is the probability, the transition probability that I get a collision between two particles in momentum p1 and p2, which gives me m particles with momentum k1 up to km, or momenta actually which are in between those values k1 up to km, and some infinitesimal variation of it. And so if I want to know, for example, all of the full cross-section that these two particles make a collision, then I don't worry about what the momentum is of the final state, and I have to integrate over all of the external momenta. So if I want to know about a finite region in momentum space, then what I have to do is take this expression and integrate over that region in momentum space. Implicitly in this expression is a delta function, which are the delta functions that impose momentum conservation and energy conservation. To make it explicit, you can also actually write down Feynman rules for these diagrams which don't involve delta functions. But so I can write down an explicit way in which the delta function is imposed. There's then a factor always in here, which is the delta function of momentum conservation. Since I have three components of momentum, I have this delta function first, and then there's a delta function for energy conservation. This is just a probability actually that a certain collision takes place in a certain region of space, and what we actually have to do is look at also not just to go to the cross-section. Actually, we have to still modify this expression a little bit, because this is not something that can be identified directly with the cross-section, and the reason is that we've chosen a particular normalization for our incoming and outgoing states. In the first lecture, I explained a bit about the cross-section, how it's related to the density of particles inside, say, a particle beam, or the current that's associated with the motion of those particles. Here, actually, we will use actually a particular set of incoming and outgoing wave functions that represent a certain incoming set of particles and an outgoing set of particles. The associated particle density you can identify indeed with the probability density and the probability currents that is associated with those incoming and outgoing wave functions. In the first lecture, I explained that if you take the relativistic wave functions of the particles, say scalar particles without any spin, then you can write down an expression for their probability density, and I wrote down, noted that the probability density for those particles, rho, is proportional to their frequency, omega over m, and the density current, J, is proportional to the momentum, P over m. And in this case, I have to worry about the incoming and outgoing momentum for the first and the second particle. So I have two densities, rho 1 and 2, depending on the frequencies omega 1 and omega 2, which I have here. So I'll call this omega 1 and this omega 2. And similarly, I have here a current J for the two particles, which depend on their momentum P1 and P2. Now, the cross-section is actually obtained by taking this transition probability amplitude, which is a probability amplitude that the collision happens per unit volume in space. I have to divide it by precisely what I call the luminosity, which was an expression which involved rho 1 and rho 2. It was the luminosity L. I wrote down as the product rho 1 J2 minus rho 2 J1. And if you take these expressions, you'll find that the cross-section, d sigma, is equal actually to this probability amplitude divided by the luminosity. And if I use now these results, you find that d sigma, and this is an expression that can be used in the center of mass frame. So the cross-section d sigma is equal to dw up to a normalization which involves the energies and momenta. This doesn't really look covariant. Actually, there's a way of making this invariant and covariant by noticing that this expression in the center of mass frame can be rewritten and then transformed into any frame. This is actually equal to 1 over, this numerator at least, is equal can be rewritten as a square root of the inner product of P1, P2, sorry. Here I take 4 momenta, so instead of using a vector momentum P, I'll take a 4 momentum which involves both the momentum and the energy. Then you can write this in terms of the inner product in Minkowski space of P1 and P2 squared minus M1 squared, M2 squared. So sometimes you'll also find this expression to relate the cross-section to the transition amplitude dW. Well, anyhow, this is the way that you go from amplitudes here to cross-sections. I won't really compute any cross-sections for you. What I will do actually is describe the rules for computing amplitudes. And those rules are in fact the Feynman rules that are derived actually from this starting point where you have this expression for the amplitude in terms of the interaction Hamiltonian. Are there any questions about this point so far? Then I'll go to the Feynman rules. Well, Feynman rules, they have, it's difficult to describe them in full generality. I haven't given you a very specific Lagrangian or interaction Hamiltonian yet. So I'll just first sketch the basic rules that are, basic ingredients that are needed to derive the Feynman rules, and then I'll go to specific examples where I can explain in more detail what the Feynman rules look like. But what we have in here is an expression which involves the Hamiltonian density, and I remind you of the fact that the Hamiltonian density was a function of all the fields, the quantum fields that are introduced in the previous lectures, and in particular they involve powers of the quantum fields that create particles or annihilate particles at certain positions in space and time. And they, so if I have a number of particles in the initial state and a number of particles in the final state, then what can happen is that these interactions, they combine those particles either at the, always at the same point in space and time, but either they can create or annihilate some of those particles and add new particles. Anyhow, the way that the Feynman amplitudes, Feynman diagrams work is that we have these incoming states, then we have the interactions and then the outgoing states. But in the Feynman rules, we have to expand this, and so we can take, say, the first expression which we have, which is if we write down the exponent of some quantity, which in this case, some quantity, say, call it x. The exponent of x always starts with 1 plus x, and then we go on. So in here, x means the integral of the Hamiltonian density just once, and the first order contributions in the Feynman rules are always coming from this first term in the exponent. And so what we actually basically doing is looking at the matrix elements then of the interaction Hamiltonian between the initial and the final states. In evaluating those expectation values, we're going to make use of the fact that we know how to write down those fields in terms of oscillators, and the way that we know how to compute expectation values in this Hilbert space. So eventually you're going to end up with diagrams which look like this, where we have, say, a set of particles coming in which interact, and then there are particles coming out, and then there are interaction vertices that are coming from the interaction terms in the Hamiltonian, and then there are internal lines which are called propagators that describe actually a motion of a particle that's being created at a certain time and a certain place, and it's propagating to another point in space and time. Or if you work in momentum space, you can always associate a certain momentum with this particle. If I know the momentum of the initial states, then the momentum of this particle will always be the sum of the momentum of the initial particles that produced this single particle. Well, as I said, to write down now for you the most general rules for the Feynman rules, I have to tell you first what is the starting point where we derive those Feynman rules from. And this is actually more easily done not by going to the interaction Hamiltonian, but to go through the Lagrangian formalism. And this is something I will introduce a little later on. What I will describe now is actually this important part of the Feynman rules, which is the propagator, how that's evaluated using the formalism that I introduced. The propagator, as I said, is something that describes the propagation from one point in space and time to another point of space and time of a particle. And so it's related actually to the two-point amplitude between the vacuum. If I create a particle at a certain position in space and time, and then annihilate the particle again at a later point in time, then if I so assume that t is always larger than t prime, then this expression is what I will call the propagator. And it's denoted with delta x minus x prime, t minus t prime. Because it's always, it turns out to be always a function of the difference between the positions and the difference in time. And it's in this case where I've assumed that t is larger than t prime, because the propagator in the case that t is smaller than t prime should be defined in such a way that this operator indeed acts first. So I could also insert in here actually the time ordering that makes clear that I always should order my operators according to the order that they act in time. Now this I can evaluate writing down the full expression in terms of oscillators, and the fact that I know that I can write down the field in terms of an expansion of oscillators where the creation operator, of course, should act first on the vacuum because the annihilation operator annihilates the vacuum. And similarly here, this field should only contribute through its annihilation operators, because here first the particle is being created and then it's annihilated. Well, I won't go through the full calculation. If you use the expressions which I gave before in the in the lecture yesterday, and insert those expressions and use the fact that we know how to commute creation and annihilation operators, you'll find that this can be written as an integral over momentum space with the normalizations, the usual normalization, the 1 over 2 pi to the third. And then what you get is exponentials actually which multiply the creation and annihilation operators in here. The plane wave expressions which are inserted are part of these expansions, both for this field in terms of x prime and t prime, and this field in terms of x and t. And the fact that I have only one integration over k is due to the fact that if a particle is created with momentum k, the same particle should be annihilated, so the momentum k in these expressions should be the same. So what I get is simply a plane wave with k, momentum k, but which depends on the difference between the two coordinates x and x prime. And then in here I have omega k, and then the difference in t and t prime. And I write down here the absolute value just to indicate that indeed t should be larger than t prime, so this is a positive number. And if t is smaller than t prime, we should invert the order of these two operators, and indeed which amounts to actually changing the sign of this expression. So this is always a positive number, which is the absolute value of t minus t prime. Well, this you can rewrite using an identity. And the reason I want to rewrite is actually that here I have an integration over 3 momenta, I want to rewrite this expression in terms of an integration of 4 momenta, and I use the following identity, which you can prove using just complex contour deformation. So I'm going to introduce a 4th component to the momentum, which I call K0. And then if you take this denominator, then this complex integration between minus infinity and plus infinity can be evaluated just using complex contour deformations and picking up the pole in here. You'll find that this gives you then precisely minus 1 I omega times the absolute value of t divided by twice omega. And using this identity, I can now rewrite this expression as an integral over 4 momenta d4k of e to the k mu x mu minus x prime mu divided by well, I'll pick the normalization here with 4 pi to the 4th, which is a combination of this 2 pi to the 3rd and the 1 over 2 pi, which I have here. And then in here I have k squared minus m squared plus I epsilon with a factor of I. Actually, we won't use coordinate space very often in doing our Feynman calculations, so the denominator which I have here, that's actually what's usually identified with the propagator. So I'll have a propagator in this, in the Feynman rules, which involves only, is dependent on the momentum of the particle that's here in the middle. So I have here an expression of a part of the propagator in coordinate space. I will transform this expression to a propagator in momentum space, where momentum is the k, which I'm in this expression is actually the momentum k of the particle that's being propagated in between those 2 points in the Feynman diagrams. So let me now come to a more general description of how you define the Feynman rules, and actually starting from the Lagrangian. The denominator which I have here, which is k squared minus m squared, so I'll write down actually once more this final expression for the propagator, and I'll write it down in a 4-dimensional notation. So in covariant notation, so x is now the 4 components, x mu being both place and time. Then the propagator, which was a function of only x minus x prime and t, so I can write it as a function of one variable, x, is then this integral d to the 4k over 2 pi to the 4th, and then a plane wave, and then there's delta of k, where delta of k I'll identify actually with my propagator. And so that's I over k squared minus m squared plus I epsilon. For Fermi, this is actually for spin 0. For fermions, spin 1/2. Well, I can actually go through a very similar calculation where I have to use the expansion of the field psi, which I gave yesterday, and then you have to insert also the fact that you know what these wave function, these spinners, the spinners UA look like. Actually, if you write down the expression for the propagator, since I create a particle and then destroy a particle, I have two spinners I have to introduce. And actually, the fact that you know the precise expression of these spinners is helpful in evaluating the propagator. I won't describe it here, I'll just mention the result. So for spin a half, you'll have a similar expression, except that the delta of k is, again, a ratio of the same sort. There's an I and the same denominator. But from the spinner part, you'll actually get a numerator which involves the gamma matrices. You'll get k dot gamma plus n as part of the propagator for fermions. So for fermions, we have a different propagator than for bosons. And even for spin 1 particles, the propagators will again look different. So which propagator you have depends on, of course, what particles are being created in the internal lines. So I will actually leave aside now quantum fields for a while and also leave aside the full description for the Feynman rules. I'll come back to that later once I started with Lagrangian field theory. So the next topic I want to describe is Lagrangian field theory, because that's the starting point that usually is used to derive Feynman rules and finally write down the expressions that you need to evaluate these amplitudes. Yesterday already indicated shortly in a brief way how to go from the Hamiltonian to Lagrangian. The Lagrangian formalism is better or easier also because all of the symmetries that we'd like to have are more manifest in the Lagrangian formalism. And once you know how to go from the Lagrangian to the Feynman rules, there's no need to go through the Hamiltonian formalism again. So a Lagrangian is just like a Hamiltonian, can be written in terms of a Lagrangian density. So we have what's called the action S, which is going to play the role of, well, the starting point of any field theory actually, because we're going to, once you know what the formalism is, you start your field theory by writing down an action. And the action is written as an integral over 4-dimensional space of a density, which I call the Lagrangian density L, which is a function of the fields phi of x and its derivative d mu of x. So I'll start with a simple case again where I have only fields with spin 0 and without charge. And then there's what's called the action principle, which is the fact that the action is minimized, or that the variation of the action should vanish in order to give you the classical field equations of motion. So the action is stationary, which means that under infinitesimal variations of the action should not change. And that should give you the classical field equations of the field phi. So suppose I take this action and vary the field phi a little bit. So actually the action principle is a variation principle that if I change phi to phi plus delta phi, then the action S will change to S plus delta S. And the action principle says actually that delta S should be 0 once the classical field equations are satisfied. So let me write down the variation of S. The variation of S, delta S, if I vary the field phi by changing the field phi plus some small variation delta of phi, what you get is that the action, well, I vary the action inside the integral, so I vary phi and I vary the derivative of phi, so there are two contributions. I get a contribution, if I vary this using just the chain rule, I can vary phi and I get the derivative of the Lagrangian with respect to phi times the variation of phi of x. And I can also vary the derivative of phi, so I also get a contribution which is the derivative of the Lagrangian with respect to d mu of phi times the derivative of the variation of phi. And this is all inside the integral. So there's one thing I would like to do more, namely is to take this differential which acts on the variation of phi of x and do a partial integration so that this derivative acts now on this factor which multiplies it. So I can, after a partial integration, write this as in the following way, where I have dl d phi, so coming from the first term, and then minus d mu dl d mu phi multiplying the same variation delta phi of x, because what I've gained by doing this partial integration is that both terms are multiplied with the same delta phi. So I've taken that outside of my bracket. So I have two terms together which now give me the variation of the action delta S. Gives me some arbitrary function which is the variation of phi times this expression. And so imposing now the variation principle that indeed the variation of the action is equal to 0 gives me a field equation, and the field equation is precisely that this expression should vanish. So the field equations are, this is called actually the Euler-Lagrange equation. So this object is called the Lagrangian, and the equation we get is called the Euler-Lagrange equation. Actually describes the field equations, and it tells you that d mu of dl d mu phi minus dl d phi is equal to 0. Sorry, I'm putting my brackets wrong. It's d mu of dl d mu phi minus dl d phi equals to 0. Well, this may look somewhat abstract, but I'll write down now quickly a concrete example. I already wrote down for you the field equations that the fields satisfy, the Klein-Gordon equation and the Dirac equation. And indeed, the Klein-Gordon equation can be derived from a Lagrangian of this sort. So the example, the simplest example we have is for the free Klein-Gordon field. The Klein-Gordon Lagrangian. So we have a Lagrangian L, which is a function of phi and d mu phi, and it's going to describe a particle without interactions, but with a mass m and without spin or charge, and L of phi in that case looks like 1/2 d mu phi minus 1/2 m squared phi squared. And if you take this Lagrangian and insert it into the equation which I have here, then you read off indeed that from here that the L d phi, which means differentiating this expression with respect to phi, is equal to minus m squared phi, and the L d mu phi, well, just comes from here. If I differentiate with respect to d mu phi, it gives you d mu phi. And the fact that the factors of 1/2 drop out is, of course, that differentiating the square gives you a factor of 2, and here actually you also recognize the square of the derivative. Now, if you take these two expressions and insert them in here, then for this example, you get d mu of this derivative, which is indeed d mu phi. So in here you find that the Euler-Lagrange equation for this situation gives you d mu of d mu phi minus, and then I have minus m squared phi, which gives you then a plus m squared phi if I take this expression and put it in here. And this indeed is nothing but the Klein-Gordon equation. And it describes a particle without interactions because the Lagrangian is quadratic in the fields, and interactions then should be introduced by adding terms to the Lagrangian, but still terms which can be written in this way as functions of the fields phi and its derivatives, so that eventually we find the full action as an integral over a Lagrangian density. So in the Lagrangian formalism, it's automatically that interactions take place locally in space and time, and furthermore it's automatic that things are Lorentz invariant, because this expression is automatically invariant under Lorentz transformations because you've written it in terms of space and time in a covariant way, and the fields phi and d mu phi are really fields that transform in the right way under Lorentz transformation. So this is a Lorentz invariance is manifest in this formalism, which was not the case in the Hamiltonian formalism which I described before. So here I wrote down the Klein-Gordon field. There are other Lagranges, of course, that you can write down. We also discussed already the spin 1/2 field, the Dirac field, and the Dirac equation can also be derived from an action principle. So I'll give the Dirac Lagrangian as well. So for the Dirac field, we have the particles for spin 1/2 are described by a field psi, which is a 4-component spinor field. So I'll have a Lagrangian, which is a function of psi and d mu psi. And for the Dirac field, this Lagrangian is equal to psi bar, and then there is minus I gamma mu d mu minus m times psi. And I'll leave it to you to verify that if you indeed insert now the Lagrangian is a similar expression where we take, of course, the same expression, but now the action principle should also involve the variations of psi. So I'll vary psi by adding a small variation, and I demand that the action is equal, its variation is equal to 0, where the action is again written as the integral of this Lagrangian density. Then you find a similar way a Euler-Lagrange equation where instead of phi here I should write psi, and then the Euler-Lagrange equation gives you the Dirac equation. So the Feynman rules, which I started to describe over here, are actually much easily read off from the Lagrangian. And here actually I wrote down the propagators. And one way of reading off the propagator from the Lagrangian is to notice, as well, you may have noticed already, that this operator which is here, which involves k squared and m squared, so it involves in relativistic notation the 4 momentum and 4 momentum squared and the mass squared, is actually nothing but the kinetic operator, the operator which is inside here in the Euler-Lagrange equation. So the Klein-Gordon equation involves d mu plus m squared on phi equals 0, but if I go from coordinate space to momentum space, what you have to do is insert d mu going to I k mu, and then you find that this operator in momentum space is nothing but precisely this combination. So there's a relation between this in momentum space and the other, the kinetic operator, d mu plus m squared in coordinate space. And this actually is the inverse, because we divide it like 1 over k squared plus m squared. So this operator actually is the inverse operator for the kinetic operator. And similarly here, actually, for the Dirac field, this propagator is the inverse of the operator, which is the kinetic operator. For the Dirac field, you can write down this also alternatively as 1 over k dot gamma minus m plus I epsilon. So it's the inverse of the operator that's in the kinetic in the Lagrangian, because k mu gamma mu minus m, I think, yeah, must be related to the operator which I have in there, which is I gamma mu d mu minus m. I may miss the sign in here, to be honest. I'm not sure. I'm not sure about the sign in. Let me think. Anyhow, the relation between the kinetic operator and this operator should be clear. And so the step from Lagrangian to the Feynman rules involves writing down the Feynman propagators, which are the inverse of the expressions which you get if you write down the kinetic term in terms of momentum space. And so I'll end with some slides which give you the Feynman rules in those terms. Can I switch it on here? How does it work? So I have here the Feynman rules for a very general Lagrangian, where I give you the basic steps that give you the propagators, but also the interactions. And interactions come from higher order terms in the Lagrangian, so where you have higher powers of the field phi. And from the form of the Lagrangian, you can then write down or read off what the contributions are that you have to include in your Feynman rules. Well, slowly it will become visible, I hope. So we have the Feynman rules, and the way to derive, first of all, the propagator and is to write down the action in Fourier modes. So instead of going to coordinate space, we take our Lagrangian and transform it into momentum space. And then you can read off from the quadratic expression, which is then written in momentum space, the form of the propagator. So if you take the form of the Lagrangian and then write down the fields phi as in momentum modes k, then there's a differential operator, usually like the differential operators which I had there, these d mu squared plus m squared, or the Dirac operator, which gives you some polynomial, some expression in terms of k. And it may be possible that these fields phi have certain indices I and j, so this kinetic operator may actually be in general a matrix. For real fields, we have to demand that phi star is equal to phi minus k, but for complex fields, this is not necessary. And then there can be interactions which involve higher powers of those fields. And again, I've written the fields in momentum space, and the form of the interaction vertices also can be written in terms of momentum variables. So if there are derivatives in the vertices, this means that we have to insert in momentum space certain powers of the momentum k. Eventually, everything is written as as integrals over these momenta, and there can be various integrations in here, depending on how many fields I have in my interactions. So for the kinetic term, I have only one integration, but for interaction terms, I can have several integrations over momenta. Now, the propagators, as I said, are determined from the kinetic term, and they are basically the inverse of this operator k, which is in the middle of the kinetic term, up to some normalization. Actually, these normalizations are somewhat convention dependent, because there are ways of changing the Feynman rules which don't change the final expression for the Feynman amplitude. Anyhow, this is a convention that you can use. And similarly, for the vertices, I write down an expression which I read off from the Lagrangian. I insert for a vertex precisely the term which describes the interaction in momentum space. So I strip off the field which I have here. I just keep the momentum part, the interaction part, which depends on those momenta. And that's the expression that I write down for a vertex. So I have lines, which are the propagators, and vertices. And then the basic rule is to connect the lines with the vertices. Of course, in writing down the scattering amplitudes, we also have external states, and those states you can actually also introduce, or in the Lagrangian, by writing down certain external sources. And so I'll write down actually a source line, which in the Feynman rules plays the role of a point where a particle is being created, and I insert for that an expression which I call ji of k. And then the rules are like this. We make diagrams. All diagrams should be allowed that connect external lines. So these are the external lines that are connected to those sources via propagators and vertices. So I have a set of external lines, and which gives me actually the number of particles that come in and the number of particles that come out. So for both incoming and outgoing particles, I add a source, and then via propagators and vertices I connect those external lines. Then there are tree diagrams which have no closed loops and where the momenta of each propagator is uniquely determined by the momentum conservation at each of the vertices. So those are the easiest processes. Then there are loop diagrams where there are closed loops inside the diagram where there are certain momenta which are undetermined, and those momenta have to be integrated over, and they're sort of often called loop momentum integrations. So eventually we have the expression for a diagram which includes the integral over the momenta, and then we have to sum over all distinct diagrams with the same configuration of external lines. And the most sort of tricky part is always this combinatorial vector. You have to sort out what number of inequivalent ways you can connect those vertices, and that's a factor that you have to include in your expression for the Feynman diagram. And then there's a subtle distinction between fermions and bosons. Fermions have different statistics from bosons in the sense that their Fermi statistics gives you a minus sign when you exchange the two particles, and actually in fermion loops you also have to add minus signs with respect to the boson expression. So in summing up diagrams you have to be sure that you sum them up with the right relative signs so that you get the right final answer. And for fermions, it's this sign that's important in doing those integrations. So finally, you have to do the integral, and that's what gives you the expression. And this is very complicated in general. Only for the most simplest cases you can do those integrations explicitly. But the rules themselves are very precise and give you closed expressions for those diagrams. So next time, tomorrow, I will start from a very simple Lagrangian, the Lagrangian of quantum electrodynamics, write down the Feynman rules and do some of these integrations for you as an example. So I'll stop here. If there are any questions, I'd like to know. No questions so far.